All right, good afternoon. Welcome back. Let's get started. I have not looked at the exam yet, so I don't have any feedback. But let's see. Do you guys have any feedback for me about the exam in terms of like the difficulty level, the how long it took you? Any comments? All right, I hope you all had enough time to work on it because I didn't really hear anyone complaining about the about running out of time. But if that was the case with you, you should let me know either. Well, you should let me know either through office hours or just send me an email. Or if you have any other concerning questions about the exam, send me an email, and I'll definitely consider those comments you sent me. All right. I don't think there was any problems that we did not cover. So it looks like well, when I wrote the exam, and I did try to kind of cover a variety of problems and I try not to make it difficult. So if you have any disagreement, again, just let me know, and I'll read it and I'll consider what you said. I mean, what you say. Okay. All right. Just kind of a quick heads up. We're going to have a quiz coming up next Monday, I believe. So quiz Monday, and that's going to cover all the material we're going to talk about today and tomorrow. So that will be full. We'll probably talk a little bit more than what's going to be on the quiz. So for today and tomorrow, we're definitely going to talk about 4.2, 4.3, 4.4, and possibly 4.5. So the quiz is going to be 4.2 to 4.3. I'm pretty sure those are the sections if I wrote down them correctly. Yep, 4.2, 4.3, and the 4.4. 4.5, if we cover it this week, when it's not going to be on the quiz. So let me erase that. All right, so that was the quiz. Let's see. And I believe we're going to have another exam coming up, not this coming week, but the following Monday, after next Monday. I have to double check the dates, but take a look at the schedule I posted on my courses, the weekly schedule. All right, on that note, any comments or any issues that we should talk about here?
I just had a question.
Okay, go ahead.
When's the homework going to be available?
That's a good question. The homework will be available today, later today. I'll say probably tonight. I'm a little bit behind on this homework. It should be a short assignment. I don't think it's going to be as long as we had before, because it's only going to be on those sections that I mentioned, and maybe 4.5. The homework going to be on 4.2 to maybe 4.4 and possibly 4.5.
All right, thank you.
Yeah, good point. I don't think it's going to be a long assignment. I'll definitely keep that in mind because obviously I'm not publishing it on Monday, right? It's making it available Wednesday night. That I'm giving you less time to work on it. I'll keep in mind that to make sure that the length is not ridiculously long. Good point. All right. Any other questions or comments? Okay. Well, on that note, so I'm just going to get started because I'm not hearing any questions or comments. So today we're going to talk about graphing exponential functions, and then we're going to talk about logarithmic functions. But recall we had exponential functions as the form of y equal, I'm going to use f of x equals ab to the x, right? Where a is just a coefficient. This is the coefficient. And the b is the base. Now, the value of A and B will decide what the graph looks like. If you remember, we had these two graphs when we first talked about exponential functions. If A is positive and the B is more than 1, the graph is going to be exponential growth. So it looks like this goes through this point, this y-intercept, there's a 1, 0, and it always has this horizontal asymptote. And if A is positive, but B is less than 1 but more than 0, so the B is always going to be positive, the base. So we're going to have this exponential decay. Again, it goes through this y-intercept, 1, 0, and has a horizontal asymptote. So to generalize, doesn't matter what B is, exponential functions always have a horizontal asymptote. Functions always have horizontal asymptote at y equals 0. But obviously, if we take the function and then we shift it up and down, that horizontal asymptote is going to be different. But if we just talk about f of x equals a times b to the x, it's always going to have a horizontal asymptote at y equals 0. And it's always going to go through this. Wait a minute, I made a mistake here. So let me fix this. So this y-intercept is not 1, 0. That's for, how should I fix this? That's a, 0. This is also a, 0. So the a value is the initial value, 1, x equals 0. Sorry about that. So it's always going to have this y-intercept at a, 0. And then we can talk about the domain and the range. So the domain of exponential functions in the form of a times b to the x is always going to be from negative infinity to infinity. But pay attention here. So this is a interval notation. When we talk about an interval of x values, but the one above it is just a point, right? The xy coordinate of this point. So we use a parentheses. So the parentheses here are used differently. So that's a domain. And the range for y equals a times b to the x, it depends on the a value. If a is positive, we get the two graphs above. So the range is going to be from 0 to infinity. But if a is negative, we just have a reflection over the x-axis. Then we're going to have from 0 to negative infinity to 0. That's a better way to write it. So it depends on what a is. So what I wrote above, the two graphs are both for a positive. So we have the first case. The range is from 0 to infinity. So those are the graphs of exponential functions. Any questions? All right. So now let's graph some functions. But before I do that, I just want to note that usually we set a equals 1, so f of x equals b to the x with a equals 1 there. So f of x equals b to the x, this is called the parent function. Means the simplest exponential function or the most basic exponential function. So this is the parent function of exponential functions. For example, the one we had above, f of x equals a times b to the x. So it has this b to the x part, the exponential part, but then we just take that, multiply by a coefficient a. So we get a new function. But generally speaking, the b to the x is considered the parent function. So here's the example. So let's graph f of x equals 3 to the x. So how do we plot it if we don't have a calculator? Well, note that b is equal to 3, which is more than 1, and the a is not here, but it's really 1 times 3 to the x. So a is actually 1, it's positive. So eventually we should get the graph on the left with a positive, b is more than 1. But let's graph it. Let's try to be as accurate as possible. So what we do is we're just going to graph at least 3 points. So make a table with x and y, and then we're going to pick some x values and to try to find the corresponding y values. So let's see, we're going to pick x equals, obviously 0 is a good number, 1 is a good number, 2 is not that bad, but usually we pick numbers on either side of the x equals 0. So we're going to pick x equals -1, 0, and a +1. Let's plug in -1. So y equals 3 to the -1. And if you remember the properties of exponentials, negative exponent means you put in the denominator. So that's a 1/3. That corresponding to x equals -1. If we put 0 there, we get 3 to the 0. Any number raised to the 0 power is always going to be 1. And if we put 1 there, we get 3 to the first power, which is 3. So now we have 3 points. We can graph those points. So that's going to be -1. This is -1 and then 1/3. Let's see, this is 1, 1, 2, 3. So 1/3 is pretty small. So let's put a point there. So that's -1, 1/3. And 0, 1 is this point on the y-axis. And then 1, 3, which is this point, that point. And now we're just going to draw a nice curve through those 3 points. But remember, it's an exponential function, which means it has a horizontal asymptote at y equals 0. So that means the graph is going to approach this x-axis. And now if we connect the 3 points, but make sure that it approaches this x-axis. So that's what the graph looks like. F of x equals 3 to the x. 3 points enough. You don't need to graph more than 3 points. So generally speaking, just pick points close to 0 and pick like a really nice point. For this specific function, we can see, okay, we can talk about the horizontal asymptote. Again, it's going to be y equals 0. And y-intercept is going to be 0, 1. Wait a minute, did I label? Oh my goodness, I don't know what's wrong with my brain. Sorry, I labeled the y-intercept incorrectly above. So that's not A0, it's 0A, because x has to be 0 for y-intercept. Goodness. So that's a 0A, Jesus. 0 for x, y equals A. So the graph above. Sorry about that. So that's the y-intercept. And we can talk about the domain. So the domain is going to be from -infinity to infinity. And the range, as you can see, the graph is everything above the x-axis. There's no x-intercept there to pass. So the range is going to be from 0 to infinity, and it never gets to 0, so we use the parentheses on the left. All right, any questions about this example and plotting it? Okay, sorry for the errors with the y-intercept. That was a stupid mistake. All right, so now we're going to look at some exponential functions and their transformations. All right, so let's see, given. So graph exponential functions through transformations. Just like any functions, we can always find a parent function, transform it to get a new function. For example, we're looking at f of x equals b to the x minus h in the exponent. So we subtract h from x plus a k. And if we have something like this, let's look at b to the x first. So that's a base, that's a parent function. That's what we start with. And if we subtract h from the x, so that means we're doing something to the x value, right? If you remember with quadratics, when we have x minus h or absolute value, when we have x minus h, we shift it to the right. So with this minus h here, we're going to shift it left or right. If h is positive, for example, x minus 3, we move it to the right. If h is negative, x minus the negative 2 become x plus 2, we shift it to the left. And the k here at the end, because we're adding a number to the b to the x part, right? We add it not to the x, we add it to the entire expression b to the x. So the k is shifting up or down because we change the y value when we add it to b to the x. So this is the shift up or down. Okay. So let's look at the example. So graph f of x equals 3 to the x minus 1 plus 4, and find the horizontal asymptote, y-intercept, domain, and range. Okay, so here we have f of x equals 3 to the x minus 1 plus 4. So let's look at it. The parent function is an exponential function. It looks like it's going to be 3 is a base, and then 3 to the x. That looks like the parent function to me. So we're going to take that function, we're going to do some transformations to it. And the minus 1 tells me that I'm going to move it to the right by 1 unit. And the positive 4 tell me that I'm going to move it up 4. So let's begin with the quick sketch of f of x equals 3 to the x. Earlier we had this, looks like this, with a horizontal asymptote. I want to erase this, probably again below. With the horizontal asymptote, y equals 0. This y-intercept is 1, 0, sorry, 0, 1. And then we have 2 more points, right? Which is 1, 3, and then negative 1, 1/3. Okay, so now let's talk about those transformations. We have 2. One is move it to the right by 1. So if we move this graph to the right by 1, if we shift it to the right, does the horizontal asymptote change? No, it doesn't, right? Because it's still a horizontal dotted line in the same place. Even if we shift it to the right, it's still in the same position. It's still the same line. It doesn't go up or down. It doesn't go anywhere. So it's the same line. Horizontal asymptote doesn't change. And at this point, 0, 1, if we shift it to the right, that's going to be at 1, 1. And the 1, 3, if we shift it to the right, it becomes 2, 3. And the negative 1, 1/3, if we shift it to the right, it becomes a 0, 1/3. So we end up with this graph. This is 3 to the x plus 1. Sorry, 3 to the x minus 1 when we shift it to the right. And then what we have to do is we have to shift it up 4 units. I'm going to move this whole graph down so I have enough space to move it up 4 units. And now we move everything up 4 units. Let's see. When we do that, when we move it upwards, the horizontal asymptote will be moved. So currently it's located at y equals 0. So when we move it up 4 units, so that will be, should be at y equals 4. So that's a 3. So let's see, 3 is here. 1, 2, 3, 4. So that dotted line, the horizontal asymptote will be now at y equals 4. And all the points will be moved up 4 units. So this is 0, 1/3, that's going to be 0, 3 and a 1/3. The 0, 1 will be moved up to 0, 4. Oh, sorry, 0, 5 when we move up 4 units. So 3, 4, 5, 6. So that will be 0, 5. And then the 2, 3 when we move it up will be 2, 7, 5, 6, 7. So now we have those 3 points. So this is a 3 to the x minus 1 plus 4. This is the final graph. But just remember that when we move it left and right, the x values, they change, but the y values, they stay the same. But we move it up and down, the y values will change, but the x values will stay the same. So now if we find the horizontal asymptote, we know that the horizontal asymptote has changed. Now it becomes y equals 4. And then the y-intercept also changed because we move the graph up and also to the right. So now the y-intercept is going to be at this point, which is 0, 4 1 to 1/3, 4 1 to 1/3, and then the domain also changed. So the domain, the domain has not changed. It's still going to be from negative infinity to infinity. And the range has changed. Now it's going from 4 to infinity because we shift the whole graph up 4 units. All right, any questions on this? Okay. So that's a graph with the vertical and the horizontal shifts. Now we can talk about horizontal vertical stretch and the compression and also reflections. So vertical stretch and compression. So that is usually multiplied the function by a number, right? So if we begin with parent function, f of x equals b to the x, and if we take this, we multiply by a number. So the new function g of x, it's going to be a number a times b to the x. So the a, the coefficient, is actually the vertical stretch or compression factor, depending on what a is. If a is more than 1, so we get a vertical stretch. If a is less than 1, between 1 and 0, we get a vertical compression. Just like all other functions that we work with. So if you take the parent function, multiply by a number in front of it, it's always going to be vertically stretch or compression. And similarly, if a is negative, so if a is less than 0, it's negative, we can think about a is negative 1 times another number. So we can think that a equals negative capital A, for example, where capital A is positive. So in this case, we're just going to think about A as 2 transformations. The negative means we're going to flip it vertically. So this negative means it's a vertical reflection over x-axis. And this A is just going to be a normal vertical stretch or compression. Right, so that's a vertical stretch, compression, and reflection. But what if we have a horizontal reflection? So that will be slightly different because it's when we reflect horizontally, we change the x values to the opposite number, right? So horizontal reflection will look like f of x. I'm going to call it g of x again. Nope, h of x is equal to b to the negative x. So the -1 we multiply with the x. This negative tells us it's the horizontal reflection. Because we're making all the x values negative. So keep in mind that horizontal changes happen to the x directly. The vertical changes happen to the sort of the y, the b to the x parent function. So here's the example. We're going to graph. Let's see, k of x. K just a name of the function. K of x equals -2 times 3 to the negative x. All right, and we're going to do it through transformation. So the parent function, again, we look at the base, which is 3. The exponent is -x, but I can ignore the x for now. Just think about it as 3 to the x, again, the same graph we work with. And then we can look at what each of the pieces do to the function. The negative here times x, that's going to be a horizontal reflection. Over y-axis. And then the 2 in front of it is going to be a vertical stretch. And the -1 in front of that 2, that's going to be a vertical reflection. But the bottom line is that we keep this parent function 3 to the x the same. So if I quickly sketch 3 to the x that we had before, so we got 1, 2, 3, 1, -1, 2, -2. So we had that point, this point, and the 1, 3. So we had those 3 points and a horizontal asymptote y equals 0. So we had this graph earlier. So that's 3 to the x. So now what we're going to do is we're going to take this graph. We're going to do a few things. It's up to you which one to do first. You can work on the horizontal reflection. I didn't spell reflection correct. Or we can work on the vertical reflection, vertical stretches. It doesn't matter which one goes first. So suppose I'm going to do the horizontal changes first. So I'm going to reflect over the y-axis. The point already on the y-axis, that's going to stay. The 1, 3 will become -1, 3. The -1, 1/3 will become +1, 1/3. When I reflect over the y-axis, the horizontal asymptote, it doesn't go anywhere. It's just a reflection onto itself. So we got this graph, which is 3 to the -x. And now I'm going to perform the vertical stretch by 2. You can also perform the vertical reflection. It doesn't matter. So let's see. I'm going to stretch vertically by 2. So all numbers, all the y value will be multiplied by 2. So 3, 4, 5, 6. So the -1, -3, when I stretch the y value by 2, so that becomes -1, +6. To give me this point. The 0, 1, when I stretch it vertically, it becomes 0, 2. And the 1, 1/3 becomes 1/2. So probably end up there. So now I'm going to take those 3 new points and I'm going to draw a nice curve with the same horizontal asymptote. So this graph in blue, that's 2 times 3 to the negative x. It's a horizontal reflection with a vertical stretch. And we have one more thing to do, which is vertically reflect over the x-axis. So that's going to be -1, -2, -3, -4, -5, -6. If I'm careful here, so the points are on the blue curve, I'm going to reflect over the x-axis. So we get 1 -2/3, 0 -2, and -1 -6. And when I reflect over the x-axis itself, the horizontal asymptote doesn't go anywhere, so it stays where it is. So I'm going to draw a curve through those 3 points and keep the same horizontal asymptote. So this is the final result, -2 times 3 to the negative x. Any questions? So here we can write down the horizontal asymptote. It doesn't go anywhere, even if we stretch it vertically, reflect vertically, or reflect horizontally. Because it's y equals 0, right? You can multiply any number by 0, you still end up with 0. So it doesn't change. So that's still going to be y equals 0. And the y-intercept has changed quite a bit because every time we stretch it vertically, we change it. When we reflect vertically, we change it. So the new y-intercept is going to be at 0, -2. And then the domain, it doesn't change in this part because when we stretch or reflect, the domain is still going from -infinity to infinity. And then the range also changed. So the range now is becoming from -infinity goes all the way to 0, but it never reaches 0. All right, let me know if you have any questions. Okay. So when you graph them, if you graph it by hand, just do your best. I would say that when I was grading quiz 2, there was quite a few students didn't draw the horizontal and the vertical asymptote. You have to draw those dotted lines because they're part of the graph, even though they don't give you any y values, but they shows where the arrows converge, where the function converges or approaches to. Make sure you include them. So just they're as important as intercepts. All right, the next example I have is consider f of x is equal to -2 1/4 x. And we're going to do a few things. The first thing we're going to do is we're going to sketch a graph of f of x first. And then we're going to take this function, we're going to perform a few transformations to get a new function. But let's quickly sketch this graph. So what I'm going to do is I'm going to take the parent function, so the 1/4 to the x, and I'm not going to do a lot of crazy things. I'm just going to kind of like, waving my hand-ish in this sketch. It's not very accurate because I'm too lazy to draw 3 points. But I'm just going to say, okay, so I have 1/4 to the x as my parent function, and I know what it looks like because the b is 1/4 is less than 1, so it's going to be an exponential decay, and it's going to have a horizontal asymptote on the x-axis, and it's going to have a y-intercept somewhere. All right, so I'm going to use those points. So I know that this graph, 1/4 to the x, is going to have a horizontal asymptote at y equals 0. And then it's going to have a y-intercept when x equals 0, we get 1, so 0, 1. And it's going to be exponential decay. So there will be other points, but I'm only using y-intercept. So this is a 1/4 to the x. And what I'm doing with this function is I'm going to multiply by 2 in front of it, which means we're going to stretch it vertically. When I stretch it vertically, y equals 0 stays where it is, doesn't go anywhere. The 0, 1 goes to 0, 2. So I get this graph. Probably doesn't intersect so quickly, so probably just go down like this. So this is the 2 times 1/4 to the x. And then one more thing, we have to reflect this over the x-axis because we have the negative sign in front of it. So this is the 1, this is 2. When I reflect this over the x-axis, so I get 0, 2 becomes 0, -2, and we still have the same horizontal asymptote, doesn't change, so we get this graph. So this is the latest graph, f of x equals -2 times 1/4 to the x. This is -2. That's a quick sketch. When you're asked to quickly sketch a graph, again, you don't need a lot of points. If you get the overall shape correct, get the horizontal asymptote, and then the y-intercept correct, then you should be all set. All right. So the next part to this is that we're going to transform f of x through the following steps. A says we're going to vertically compress it by 1/3. So vertical compression by 1/3. And then we're going to move it to the right. So shift right 4 units. And a C says we're going to shift it down 5 units. The question is, after we do all those to f of x, which is above, what's the formula for the new function? So what's the formula for the new function? And then can we find and what is the horizontal asymptote, y-intercept, domain, and the range for the new function? So that's what we want to do, right? Feel free to use graphs, and I'll probably do that too. So let's think about this. Before we graph it, let's suppose, I have f of x given. So f of x is -2 times the 1/4 to the x. That's given. And then suppose I'm going to take this function, I'm going to vertically compress it by 1/3. So that means I'm going to take all the y value from this function, multiply by 1/3, right? That's a vertical compression. And even if we don't have a graph, we can write down the formula for that. So that's just going to be 1/3 times this function f of x, -2 1/4 to the x. Now, this is all multiplication. So what we're going to do, we're just going to drop the brackets and multiply 1/3 and a -2 together. So that's going to be -2/3, 1/4 to the x. 1/4 is still the base. Now we just have a new coefficient, -2/3. So that's a vertical compression by 1/3. And now the next thing we're going to do is we're going to shift it to the right 4. So when we move it to the right, if you remember, it only changes the x value. It doesn't change the y, right? So whatever changes is going to be in the x part. when we move it to the right 4, so the x will change, becomes x minus 4. So the next step, so the part A is this, and the part B give us this one. So that's going to be right 4. So that's going to be negative 2 over 3, 1/4 raised to the x minus 4. So that's the right 4. And the C that's shifting it down 5. So after I've done everything, if I move it down 5, I'm going to subtract 5 from the function above. So C is going to be negative 2 over 3, 1/4 x minus 4 in the exponent, down 5, so minus 5. So this will be my new function. I'm going to call it g of x. I just want to use this example to show you, even if we start with a function that's not a parent function, not the simplest function we should have, but we can still work with it, take whatever is given, and then we're going to either multiply the y part by a number or subtract a number from the x part or subtract a number from the y part. It still works. Any questions? All right, so now we need to figure out the horizontal asymptote, y-intercept, domain, and the range. I'm going to use a graph because I cannot always do everything correctly in my head. So I'm going to take the function f of x, the blue curve here, which has a y-intercept at -2 and a horizontal asymptote at 0. So I'm going to take that function, I'm going to follow those transformations. So -2, horizontal asymptote is x-axis, so we get this graph. This is the f of x. And the first thing I'm going to do graphically is vertical compression by 1/3. So if I compress this by 1/3, so that's going to be -2/3, which is here. And when I compress it vertically, the x-axis stay the same, which means the horizontal asymptote doesn't change. All points will be compressed by 1/3. So we end up with this. So this is the 1/3 f of x. And then I'm going to shift it to the right 4. So if I shift it to the right 4 units, so this point, let's see, 1, 2, 3, 4, that point will become here. Now you probably think, okay, what is a y-intercept? Actually, I don't know because I didn't have a point on the left to draw the y-intercept. That's okay. We can figure out if we want to, but let's just say we leave it for now. So this point on the y-axis now being moved to this point. And then when we shift it to the right, the horizontal asymptote is still there. So now we end up with this graph with some y-intercept that I still need to find out. So this is a 1/3 f of x minus 4, shifted to the right 4. And then the last thing we have to do here is we have to move it down 5 units. So if I shift this down 5 units, this point will be down 5, and the horizontal asymptote will also be shifted down 5 units. So let's see, 3, -4, -5, -6. When we move the horizontal asymptote down 5, so it ends up at -5 now. Y equals -5. And at that point we had on the graph, that's going to be -5 and the 2/3. So it's going to be here. And we just have this graph. It does not pass a horizontal asymptote in this case. It just approaches it. Okay, so that's the final graph. 1/3 f of x minus 4 minus 5. So that's what this function is. And we can look at it it's a lot easier to identify the horizontal asymptote because we have it shown here. So the horizontal asymptote is going to be y equals -5. And if you want to know, okay, what is a y-intercept? How do we find it? It's not drawn because I didn't have enough points to have a point land on the y-axis when I did the shift. That's fine. To find the y-intercept, just like any function, if we want to find the y-intercept, we set x equals 0. So if we set x equals 0 in this case, we get g of 0, which is -2/3, 1/4 to the 0 minus 4 minus 5. So let's see what we have. We have -2/3, 1/4 raised to the -4th power minus 5. Now, if you remember that with the exponential properties, we can rewrite 1/4 as 4 to the -1. So we get -2/3 times 4 to the -1, and outside we still have this like -4 as an exponent, minus 5. So eventually that comes down to -2/3 times 4 to the -1, -4 becomes 4 to the +4, and minus 5. And I'm not even going to try to do this because that's quite a big number. I think it's like a 200 something, 256 perhaps. And times 2 divided by 3 minus 5 looks like it's still end up with the negative number pretty big. So I'm just going to leave it there. There's no point of calculating. So that's a y-intercept. I just want to show you if you want to find it, you always set x equals 0, unless you can pick it up from the graph. Now, the next thing we can talk about is the domain. Even if we shift the graph horizontally and vertically, the domain is still the same, going from -infinity to +infinity. The range, we have to be a little bit more careful because now it goes all the way up to -5, so from -infinity to -5. One thing I want to point out is the common error is that often students will be like, oh, the y-intercept is this number, it must be related to the range. No, so the range and the y-intercept, they're not connected at all in this function. In some functions, they might be related, but usually they're not. Any questions? Okay. All right, if you don't have questions, let's do one more example before we take a quick break. The next example I have is consider f of x equals -1/2, -1/2, 3 to the x minus 1 plus 4. So that function has a lot of transformations. If we think about the parent function is 3 to the x, right? But we're going to take this function and we're going to transform it. So f of x is transformed through the following steps. A is, what we're going to do is we're going to shift it down 4. B is, we're going to move it left 1. C is stretched by a vertical factor of 2. So vertical stretch by 2. D is, we're going to reflect over x-axis. So the question is, what is the formula for the new function we obtained? Well, we begin with f of x, and we're going to do all those. So let's just see what happens to each part of the function, the x or the y. So if we take f of x, -1/2, 3 to the x minus 1 plus 4. If this is my function, if I shift it down 4, so that means I'm going to take the y value of this function, I'm going to subtract 4. So that means I'm just going to take this, that's what the function or the y is, and then we're going to subtract 4. So that's down 4. And let's see what we end up with. Well, if we had adding a 4 at the end, now we subtract 4, so the 4 goes away. So we get negative 1/2 3 to the x minus 1. Not too bad. All right, so that's a new function we get after we move it down 4. And then the next thing we do is move it to the left by 1. Now, if we move it to the left by 1, we're going to subtract a negative 1. We're going to subtract a negative 1 from x, or we can think about it as adding 1 to the x, right? When we move it to the right, we subtract 1. When we move it left, we're adding 1 to the x value. So now in the next step, so this is A part. The B part is we're going to take negative 1/2 3 to the x minus 1. Now we only change the x, so it's only happening in the exponent. We're going to add 1. That's a good thing because minus 1 plus 1 becomes 0, so we end up with negative 1/2 3 to the x. Good. So that's B. And the C says we're going to vertically stretch by 2. So if I take this function, what we end up with negative 1/2 times 3 to the x. I'm going to vertically stretch by 2, so I'm going to multiply by 2. So I get negative 1/2 times 3 to the x. I'm going to move it, take this function, vertically stretch by 2, so I'm going to multiply by 2. And if I simplify that, 2 times 1/2, that's 1, but I still have a negative, so I get negative 3 to the x. And the D says we're going to reflect over the x-axis. When we reflect over the x-axis, we make the y negative, right? So we basically add a negative 1 in front of the y, the function. So we get negative of negative 3 to the x. We end up with positive 3 to the x. So after those transformations to f of x, we kind of end up with the parent function, 3 to the x. So we basically undone all the transformations that happened to the parent function in order to get f of x. We can just do the whole thing backwards. I just want to use this to show you that even if we give any function and we want to know, okay, the function went through this transformations, what do we end up with? You can do the same thing without graphing. Just decide what's the appropriate number to multiply, to add, and where to multiply or add those numbers. If it's happened horizontally, you only do it to the x. If it happened vertically, you do it to y, which means the entire expression. All right, questions? Okay, 7:03. So let's take a quick break. Let's come back here at 7:10. So break until 7:10. I'll see you in a few minutes. All right, welcome back. So the next thing I'm going to talk about today, here we go. So the next thing I'm going to talk about today is logarithmic functions. I'm sure we all have our struggles with logarithmic functions. Now, I want you to think about logarithmic functions that kind of like the inverse of exponential functions. They are actually inverse of exponential functions. So they undo those exponential functions. So for example, so recall the parent function of exponential functions could be y equals or f of x, y equals b to the x. Now, so it takes the x, does the exponential part, and it gives us a y. But if I want to undo that, if I give it a y and I want to end up with x, so that's where logarithmic functions come in. So if we do that, so the inverse is going to be y equals log base b of x. Now I'm using y and x here, so but be careful, this y and this y, the x are different. They're not the same x, y. So not same x and y, because when we find the inverse, we switch them, right? But let me kind of change my notation, make it more appropriate. So rewrite y equals log base b of x. If we keep the same x, y, that has the exponential form of base b raised to the y equals x. So now the y and x, I'm not changing them, I'm just rewriting them. So same x and the y, just rewriting the terms. The function. But you should think about the logarithmic function is really the inverse of exponential function. Even though when you write it down as inverse, it looks different, but they're really the inverse. But suppose I'm not thinking about them in terms of inverse, I'm just thinking about, okay, this is a one form, exponential form of the function, and I'm going to rewrite it by moving the terms around and to follow the appropriate rules. I end up with this one on the left. So that's just rewriting it. This is the equivalent. They're not the inverse, they're equivalent. Right. So that you can think about this is one way to kind of to rewrite the logarithmic function into something more familiar, exponential. So how do we read this? This one, we can read it as y is, not y. So y is log base b of x. So the x is always considered inside the log. And the base b with the log, that's always together. So never try to think about, they're separate parts. So log base b is always like one entity, kind of like a cube root or square root, right? So if you write cube root, the 3 and then the radical notation, they're really together. They're not separated. So same thing with log with the base, they're together. They're not something you can separate. So that's something to keep in mind. So this is the one part. Don't try to separate them. All right. So what's the graph look like? We're going to talk more about graphs with logs next time. So graphs of logs. So generally speaking, the graphs of logs and exponentials, since they're the inverse. So let's just say we take this example. This is the exponential function y equals b to the x with b is more than 1. And if we take that function, we reflect over this line, y equals x, the reflection is something that looks like this. So this y-intercept becomes an x-intercept. The sort of the negative axis part becomes the negative y part, and the fourth, whatever is in the first quadrant still stays in the first quadrant. So this blue function is y equals log base b of x. They're the inverse of each other. And this one has a b that's the width b more than 1. Now, what if b is less than 1? Then we end up with a slight different graph, looks like this. So this is a y equals log base b of x, with b is less than 1, but b must be positive. So that's the two graphs with logs. So one is this kind of like an increasing across the x-axis, one is decreasing across the x-axis. So for y equals log base b of x, the b is always going to be greater than 0, and b is not going to equal to 1. We can talk about the x-intercepts. In this form, log base b of x, so that's always a x-intercept, which is at 1, 0. And there's always a vertical asymptote at x equals 0. So the vertical asymptote is its y-axis. And we can talk about the domain. So the domain is going to be from 0 to infinity. So the domain is always going to be positive if you think about where the domain is. So this x here in the log base b of x, so this x here, it must be positive. So that's what the domain part says. So inside the parentheses of log base b in here, it's always going to be a positive value. Always. You cannot have a negative number inside the log. We're going to have a problem if we have a negative number in the log. We cannot even find it. So always a positive number inside the parentheses of a log. And the range, it's going to be all real numbers. So from negative infinity to infinity, it continues on both ends. So that's with logarithmic graphs. We're going to talk more about this next time. But I just want to kind of give you those key features about those graphs. All right. So the next thing I want to quickly mention about common logs and the natural logs. So note, when we have y equals log base b of x, so b could be any number, that's more than 1. Sorry, that's more than 0, and that's not equal to 1. So b could be any number. If we have b equals 5, we write log base 5 of x. B equals 100, we write log base 100 of x. But commonly we use, so often we use b equals 10 or b equals the natural number e. Then we can write y equals log base 10 of x. But because we use it so much, we don't really want to say, okay, log base 10 all the time. So we can just write log of x. So there's no base showing up. So there's no number at the bottom of log. It just means that's a 10. And same thing with base e. So y equals log base e of x. Because we use it so much, we don't want to write log base e the whole time. We just use natural log ln of x means log base e. So if you see those two common logs, you should know what they refer to, what the base are. All right. So that's some notation with logs and that common logs. All right. So the next thing we're going to do is we're going to convert from exponential to logs and from logs to exponential. And from log form to exponential. Okay, so how do we do that? It's literally going back to the sort of like the definition part. So if we have y equals log base b of x, we can rewrite it, become b to the y of x. So that's from log to exponential. If we want to go backwards, it works the same way. So for example, I'm going to ask you to rewrite this. So log base 2 of 32 equals 5. So this is a exponential equation. We can rewrite it by converting this into a, sorry, this is a logarithmic expression. We can convert it to exponential. How do we do that? Well, the way I remember is the base, whatever the base in the log base 2. So the base always stay as the same base. So base 2 in the log stays as base 2 in the exponential. And we just need the exponent and then need something on the other side. Well, what goes into the exponent? Well, those two parts, I think about them as kind of like switching the place of those two. So in the log, whatever is inside the log next to the base 2, in the other form will be away from the base. So 32 is next to the base 2. In the exponential form, 32 will be away from the base 2. And whatever was away from the base, now it's actually being put next to the base. So the 5 will become the exponent. So 2 to the 5th equals 32. That's equivalent to say log base 2 of 32 equals 5. Does that make sense? So I always pick the base first, and then I just look at two parts. If it's next to the log, I'm going to put it away. If it's away from the log, I'm going to put it next to the base. Another example, 10 to the negative 4 equals 1 over 10,000. And that's an exponential form. We're going to convert it to log. What we're going to do, again, I'm going to pick the base. So the base here is base 2. Sorry, it's base 10. So when I convert to the log form, the log is going to have a base 10. So log base 10. Okay, good. And the next thing I'm going to do is whatever is next to the base, negative 4 in this case, I'm going to put it away from the base in the log. So that's going to be negative 4 on the side. Now, what about the other side that's away from the base 10? Now I'm going to put it actually next to the log, next to the base. That's a 1 over 10,000. So this negative 4 and this side, they switch places in terms of the base. So that's just how we rewrite those equations. Literally just make sure the base is still the base, but just flip the other two parts. All right. So the next thing we can do is evaluating logs. For example, evaluating logs just means finding the equivalent answer, equivalent value. So if I give you log base 3 of 1 over 81, I want to know what that equals to, right? And it's in the log. Obviously, if we have a calculator, we can put into the calculator. Suppose we don't have a calculator. How do we figure out this number that's equivalent to? Well, I don't know. I'm just going to begin by calling this number x or y, right? So let's just suppose that's x. And if I know what x is, then I have the value, the answer. So if I put the x there, and I get an equation, which means I can take this log equation and I can rewrite it as an exponential. So the first step is just call it x and then change the form. So now I'm going to rewrite this as exponential. So the base is 3, so that base 3 doesn't change. And then I have 3 to some expression equals something else. Well, that will come from switching this part inside the log and this part away from the log. So the x was away from 3. Now I'm going to put it next to 3. So 3 to the x. 1/81 was next to the base 3 in the log. So now it becomes a 1/81. Okay, so 3 to what power equals 1/81? I still don't know. That's okay, but at least this is like exponential, right? It might be a little bit easier to accept because we probably more comfortable with exponential equations than logarithmic equations. So let's see, maybe we can rewrite 1/81, and that probably becomes 81 to the -1. And let's think further. Okay, 81, can I convert it to 3 to a power, right? So 3 to what power give me 81? Let's see. Okay, 3 to the first power is 3. 3 squared is 9. 3 cubed is 27. And maybe 81 is 3 to the fourth power because that's 9 times 9. That's like a 3 squared times 3 squared. So that's a 3 to the fourth power to the -1. This becomes 3 to the -4. And on the left side, I get 3 to the x. So in total, I have 3 to the x power on the left and 3 to the -4 on the right, and they're equal. So that means x must equal to -4. So that's what this x value is, -4. So as n, I'm going to write log base 3 of 1/81 is equal to -4. That's how we end up with the value for this logarithmic expression if we don't have a calculator. Any questions? Okay. All right, we can look at a couple more examples on this. The next example I have is we're going to evaluate log of 1,000,000. Again, I don't know what it is. I'm just going to call this x. And the next thing I'm going to do is I'm going to rewrite it from logarithmic expression to exponential. Okay, so what is a base? Looks like I don't have a base, right? But remember, this is one of the case that if we just have log, it doesn't have a base, which means there's a base 10. So in the exponential, I have to have the base there. So base 10 to some exponent is equal to something else. And we just have to replace or switch those two parts. One is away from the log, one is next to the log. We're going to flip those two when we convert to the exponential. So I'm going to put x as the exponent of 10 because it was away from the base 10. And I'm going to put 1,000,000 on the other side. So 10 to what power give me 1,000,000? Well, there's 6 zeros in 1,000,000. So I can write 10 to the x is equal to 10 to the 6th power. So x must equal to 6. So the process is similar to what we did earlier. All right, any questions? Let's look at one more example if you don't have any questions on this. So example, I want to know what is the natural log of -5. And some of you probably look at it and already know the answer. Let's suppose I don't know the answer. Let's try to find it. So I'm going to again call this x. And remember, natural log is just log base e. So we basically have log base e of -5 equals x. And I'm going to convert this to exponential. So that will be base e to the x equals -5. So it's difficult, right? Because I don't know e to what power give me -5. You probably need a calculator. But it turns out that if we think about e as a number that's like a 2.7, so it's a number between 2 and a 3. So 2 to what power give me -5, or 3 to what power give me -5? And if you think about a function of 2 to the x and a 3 to the x, they look pretty much like this. Do I ever get to -5? The answer is no. You never get a negative y value when you have 2 to the x or e to the x or 3 to the x, because it never passed the x-axis. So it's always positive. So when we have a negative number for e to the x, we're not going to be able to find the x satisfying that equation. So no such x. Another way, sort of going back to the logarithmic expression on the left here. So we have natural log base e of -5. So this is a negative number inside the log. If you remember earlier, we talked about it when we talk about the domain. So whatever inside the log has to be positive. So you cannot have a negative number in the log. So must be a positive number. If you have a negative number in the log, just say there's no such an x value. It doesn't exist. We cannot find the x. So we cannot find this x at the end. Okay, any questions on what I talk about here? I know that, this is I'm pretty sure that you all think logarithmic in the past, but it could be confusing. I hope I didn't make it worse. Let me know if you still confused about this logarithmic and exponential conversions. All right, I'm going to spend probably the next 10 minutes or maybe less on a few important properties with logs. So properties of logs. Just a list of properties. You have seen that before, but make sure you really know them like very well, because if you don't, it's going to give you a very difficult time in the maybe next couple of lectures when we talk about logs and exponentials. So the first one is log base b of 1 is always going to be 0. And then the second one is log base b of b is always 1. And we can actually, for the second one, you can actually think about this b has the exponent 1, this log base b, and the exponential base b, they kind of cancels, just give you 1, the exponent. That's one way to think about it. Which brings down to the next property, which is log base b of b to the m is always m. Again, you can think about this log base b and this base b inside the log. So in the log, we have this like an exponential part with the base b, right? And that base b and the log base b, they kind of cancels, just give us whatever the exponent m left. And the fourth property is that if we have a exponential expression with the base b, so this is base b is going to have an exponent, and in the exponent we have log base b again of some, let's see, x, for example. So outside we have this base b, and then it has an exponent, but in the exponent it has this log base b again. So in this case, you can think about, okay, this base b of the exponential part and this log base b, they cancel, they undo each other. So just give us x left. So this log base b and this exponential base b outside cancels, just give me x. Okay, so that's the log base b part. The next property is, let's see, what if we have, let's see, log base c, instead of have b to the m inside the log, let's just say we have x to the m. So x is not the same as base b anymore, it's a different base x. How do we rewrite this? Well, if we have this case, we can always bring the exponent m outside to the front of the log and turn it into a multiplication. So this becomes m times log base b of x. So the x is still inside the log, it doesn't go anywhere, but like the exponent m, we actually bring it outside and then make it multiply the log base b of x. So this is actually very useful because if we're looking for something in the exponent, when we bring it to the front, we're really not solving it for anything inside the log, we're solving it outside of the log. So this is a very important property to know. Well, all of them are important, but this one really helpful in a lot of situations. And the sixth would be the product rule, which is log base b of, let's see, x times y is the product inside the log. And then we can write this as log base b of x plus log base b of y. So we turn the product into a sum of two logs. But often we're actually going backwards. Often we're going to the left. If we have a product of two logs, we convert it into one. Sorry, if we have sum of two logs, we convert into a log of a product. And the 7, if we have, let's see, log base b of x divided by y, and that's going to be log base b of x minus log base b of y. Again, it's just like the products, now we have a quotient. So I would say the last three, the exponent, the power property, the product property, the quotient property, those three are very useful in a lot of cases. And all others are important. You know, it's not like they're not important. They're important too. We use them all the time when we solve equations, when we simplify expressions. So we're going to do 2 more examples. The first thing we're going to do is we're going to fully expand the following. Fully expand. The expression I have is going to be log base b of, let's see, well, I'm not, should I use b or should I use a number? It doesn't matter. Let's see, log base b of 3x over 2 squared. So inside the log base b, we have this 3x divided by 2, and then we have a square outside of that fraction. So note that the square is also inside the log. So everything is inside the log here. So we want to fully expand this by using the properties above. Well, the first thing we could do is we can look at this, the exponent 2. That's the exponent inside the log. So that means I can bring it directly outside. It becomes 2 times. So that becomes 2 times log base b of 3x over 2. We get rid of the exponent that way. And now I'm looking at this inside the log here. I have 3 times x and I have divided by 2. So it's a multiplication and a division. So let's look at the division first. If it's a division in the log, I can convert it into a subtraction. But the 2 is still outside. So 2 times. Now I'm going to take that log. I'm going to convert into a subtraction. So that's the log base b of 3x minus log base b of 2. But I still have this 3 times x as a product in the log. I can rewrite that as using the product rule, convert it into a sum of two logs. So I have 2 times log base b of 3 plus log base b of x minus log base b of 2. So that's fully expanded. There's nothing we can simplify. And then you probably wonder, oh, can I bring the 3 and the 2 together? Sure. Become 3/2, but it's okay. In this case, just leave it like this, fully expanded. All right, any questions on this? Okay, so the next thing we're going to do is we're going to fully condense the following expression. Let's say log base. I'm just going to use common log. I'm not even going to use a base. There's base 10 here. So log of, let's say 3x minus 2 log 5 plus log of x minus 1. So that's all I have. I'm going to condense this, means bring all the logs together. Now they all have the same base, base 10. If they don't have the same base, we cannot combine them. Okay, so look around, log 3x, then we have 2 log 5, then we have log again. So the first thing we're going to do when we condense is we take the x, the coefficient, and we make it exponent. So we all begin with like a log of something, nothing in front of it. So that becomes log of 3x minus log of 5. When I bring the 2 inside, it becomes a square, so 5 squared. And then plus log of x minus 1. So that's the first step. The second step is we can bring the terms together. If we have subtraction of logs, it becomes a division. So we have log, if we look at the first 2, the subtraction becomes log of, inside the log, we have a division, so 3x divided by 5 squared. I'm going to think about 5 squared as 25. So put the first 2 logs together, and then we're going to add log of x minus 1. Now we have a product of, we have a sum of 2 logs. So I'm going to put them together as a product. So I get log, inside the log, I have 3x over 25 multiplied by, coming from the second log, that's x minus 1. So that's what I have when I fully condense them. And we can rewrite it to make it look nice, maybe bring the x minus 1 into the exponent, but not much we can simplify. So that becomes log 3x times x minus 1 in the exponent divided by 25. That's all we can write. Any questions about how do we condense them? Okay, let's see. Do I have a calculator? I don't think I have a calculator on my computer that I can share. Hold on, give me a second. All right, do I have a scientific calculator? Oops. All right, I do have a calculator on my computer. I just want to show you how do we use the calculator to calculate. Anyway, well, actually, let me know. Can you feel free to raise your hand if you don't know how to calculate log of a number into a calculator? For example, let's see, calculator section. So suppose I say, okay, find log base 3 of 27, not 27, 20. Let's see. let me know if you don't know how to use a calculator to find this. Anyway, doesn't matter. I'm going to show you anyway. So with a graphing calculator, like if you use graph calculator in high school, like a TI-83, TI-84, TI-89 or whatever, all those, they allow you to type this directly. So in the calculator, you can actually bring this. There's one way to bring this, like sort of this function out in the calculator. Then you can just put in the base and the 20, then that give you a number when you press enter. Now, for some calculators, they don't have this. So let's say you have an older version, like a regular standard calculator. You don't have this. What you might have, the calculator might have a button that says log, or maybe like ln. You might have those two, right? But how do we use that to find out what the value of log base 3 of 20 is? So what we will need is called change of base formula. So what we do is, if we have log base b of a or x, so the base is b, x is in the log, and we can actually rewrite this by picking any base. So that could become log base, like a new base a, for example, of x, divided by log base a of b. So basically, we use the change of base formula to convert it into a division of two logs with a new base. The x and the b, they goes into the logs in the numerator and denominator. But instead of using a random base a, we often use base 10. So that becomes a log of x divided by a log of b. So that's base 10. We could also use base e. So that becomes natural log of x divided by natural log of b. So using the change of base formula, we can convert a log into a division of two logs. So the example above, suppose we just have a regular calculator. We have log base 3 of 20, and I want to calculate that using a normal calculator that doesn't allow me to type it in. So I can use a change of base formula using either log base 10 or natural log. So I can write it as, let's say, log base 10 of 20 divided by log base 10 of 3. And I can put this into the calculator, give me a number. Or I can write as natural log of 20 divided by natural log of 3. Either way, I can get the same number. But let me show you using the calculator I've had. Where was my calculator? Okay, so this is a calculator on my computer. I'm just going to use it here. I just want to show you quickly and how it works, and I'm sure you all know how to make it work. So let's see. All right, hopefully you can see the calculator on the left here. So as you can see at the bottom, we have this log and a natural log button. So if I want to use log to calculate log base 3 of 20, so I'm going to put log of 20 first. So log, oops. So log, oh, looks like I have to put into the log the 20 first. Clearly, I've never done this before. So put 20 and then press log, but you might be able to just type log and then press 20, one of the two ways. So that gave me 1.3. And then I'm going to do the same thing with log of 3. So I'm going to put 3 first and then press log. So log of 3 is 0.477. And then as you can, if you take one more step by taking 1.3 divided by 0.477, and that should give us 2.72. So that's how we use the calculator to figure out what log base 3 of 20 is, if we cannot type it in directly. All right, on that note, any questions? All right, anything about today's lesson at all? Like all the graph we did with exponential functions, the log properties. I would say one last comment. If you're not familiar with the properties of logs, you do need to memorize them. There's no other way, trust me. If you feel like you just don't have a good good memory of them, definitely memorize them tonight. Because this is going to help you a lot, not just for this class. Obviously, when you take calculus, you don't really have a lot of time to figure out what the properties of logs. You just have to know it really well. Questions, comments? All right, on that note, I'm going to let you go. We're going to finish a little bit early today. Go have some dinner, do some work that you have to do. And I'll see you tomorrow. And I'll try to post the homework sometime tonight, and I'll do my best. If not, probably tomorrow morning. I apologize for late on assignment. If it's tomorrow morning, I'll definitely keep in mind, not make it too long. All right, take care, everyone.
Thank you.
All right, bye-bye.
Thank
Take
you.
care. Yep, thank you, bye. All right, let's see, Susanna.